How can writing equivalent expressions show how quantities are related? Think about this question during the lesson. A new box of pasta claims to contain 25% more than the usual box. What expression shows the amount of pasta, P, in the new box? Begin by answering this question. What expressions can you write to represent a percent greater than the original amount? The original amount is 100%. So an amount that is greater than the original amount will be greater than 100%. To help us write the correct expression, let's draw a bar diagram to represent the situation.
All right, let's start the activity. Drag tasks to complete the bar diagram. So the original amount of pasta plus 25% more. I don't know where I'm supposed to drag them to. Here? 25. So is this the end value here? So we have the original amount of pasta plus 25% of the pasta equals the end result.
The blue part of the bar represents the original amount of pasta. We'll label it P. The red part of the bar represents the extra pasta, 25% more. How can you represent a percent as a number that can be used in an expression?
How can you represent a percent as a number that can be used in an expression? Ooh, when we're talking about using percents in equations, what do we have to do? Does anyone remember? Nobody's going to talk back. Okay, to use a percent in an equation, we have to write it as a decimal. We can't use 25. We have to write it as a decimal.
If you divide a percent by 100 and remove the percent sign, you can use the resulting number in an expression. So the orange part of the bar is equal to 25/100ths of the original amount, P. Now write an expression to represent the amount of pasta in the new box. P plus 25/100ths times P. What is the coefficient of the term P? Select your answer.
All right, this is that invisible math. If you remember, if there is no other number in front of the P, in front of a letter, if there is no number in front of the letter, obviously there are not none of them because it's there, so it can't be 0. It's there, so it has to have some sort of value. Well, how many P's are there if there's no number there? What's that invisible math? Well, there is 1. If there is no number there, it just means that there is one of them.
P can be rewritten as 1 times P. So the coefficient of P is 1. Combine like terms. 1 and 25/100ths times P expressed as a percent is 125% of P. 25% more than 100% is the same as 125%. The expression 1 and 25/100ths times P shows the amount of pasta in the new box.
Okay, why do you care? Because you care if you're trying to find out which is actually the better deal. So you would find out what the price of the regular box of pasta is and find out how much it is per gram or ounce, whatever the measurement on the box is, and then find out the price of the box plus 25% more, and dividing it by ounce, whatever, you should get the same number. If you get a bigger number, then they're lying and it's not actually a deal. If you get a smaller number, then awesome, it's a bigger deal, go with that one. That's why this matters when you're grocery shopping as an adult. So if we look at this one here, Joe is buying gift cards that are on sale for 15% off. He uses C minus 0.15C to determine the sale price of the gift cards. What is an equivalent expression that Joe could use to also determine the sale price of a gift card? Okay, what they mean by that is combine those like terms, right? We have a C and we have another C. They're both C's, so we have one C minus 0.15C. Okay, 1 minus 0.15, or we can imagine that these are, right, we're talking about percents. So we can pretend that this is 100% C, and we're subtracting 15% C. So 100 minus 15C is going to be 85C, and then we just got to put that decimal back in there. So 0.85C is going to be an equivalent expression. If you think back to when we were actually doing percents, markups and markdowns, right? One of the things that I said was instead of finding 15% of $25, if something was $25 at 15% off, right? Instead of finding 15% of that and then subtracting it, you could just find the opposite, which is 85% of $25. Right? That's kind of it's coming back around full circle, right? What we learned in percents, we're going to apply to some expressions now. It's coming back. So if you missed the percents part, make sure that you try to get it here or meet with me sometime to get it. Okay, so 15% of 25, and then we would subtract whatever that was. Instead, we can just find 85% of that. So if you're not paying for 15% of it, you're paying for 85% of it. So convince me, how do you know if an expression is describing a percent increase or a percent decrease? Oh my gosh, can you imagine all of this math relates to math that we're going to cover later? OMG. Okay, how do you know? Well, the subtraction sign is going to be a decrease. A plus sign is going to be an increase. Or just think about it. Off is another keyword. That means decrease. Mark up would mean increase. Okay, that's how we know. Because we've talked about all this before and you showed mastery and we all remember it from when we did it the first time. Example 2. Ooh.
Some middle school students will use 1-foot tiles to create a frame around a large square mural painting. 3 students each wrote an expression to determine the number of tiles needed. Are these expressions equivalent? Explain. Each student used the variable s to represent the side length of the square mural. One student divided the green border into 4 equivalent rectangles. Each side length is s plus 1, and there are 4 sides. Then the student made an area model. As the model shows, the length of the green border is 4 times the quantity s plus 1. The second student made a different area model for the green border. The student observed that each side length is s, and there are 4 sides. There are also 4 corner tiles. The length of the green border is equal to the sum of the 4 side lengths of the square, plus 4 times 1, or 4. The third student divided the green border in another way. This student started at the top and bottom lengths. This student stated that the top and bottom lengths are s plus 2, and that the lengths of the left and right sides are s. Then the student made an area model to show the sum of the 4 lengths. The length of the green border is 2 times s. plus 2 times the quantity S plus 2. The student's work shows that the three expressions are equivalent. They each represent the number of tiles needed for the frame around the painting. Look for relationships. What does each expression tell you about the relationship among quantities and variables?
Okay, so if we look at the three different ways that the students figure them out, we know that they're going to be equal if we just combine the like terms and distribute and all that kind of fancy stuff. So if we took the first one, we did 4 times S and 4 times 1. That's going to be 4S plus 4. Okay, if we took this one, here's like terms, 1, 2, 3, 4. That's 4 S's plus 4. And this one, if we distribute that 2, we have 2S plus 2S is 4S, and 2 times 2 plus 4. Okay, so for each of them, we get 4S plus 4. So as long as they're all looking at the same thing, you can write equivalent expressions. As long as you are all taking into the same account, all of the measurements are the same for each size. You can make different equivalent expressions. Let's see if we got one more. That's a good example. I'll erase this stuff. Okay, so if we look at this problem, it says a table with a rectangular top has been extended with a table leaf as shown. Multiply 3.5 times 6.5 plus S to write an equivalent expression for the total area of the extended table. What did each term of the equivalent expression tell you about the table? Okay, so if we multiply, if we distribute 3.5 times 6.5, we're going to get, 3.5 times 6.5 is 22.75 plus 3.5 times x is 3.5x. Okay, that's what multiply that. Well, we wrote an equivalent expression. It's right here. What does each term of the equivalent expression tell you about the table? Okay, what does the 22.75 constant mean? And what does the 3.5x mean? Okay, the 22.5 is the area of the original table. So this is the area of original table. And what does this mean? Well, that is the area of the leaf. Okay, that's what they tell us about the table. The first one tells us the area of the original table. The second one tells us the area of the leaf. Oh, yep, didn't work there. There we go. We look at the next one. There we go. There it is. The area of the original table is that. The area of the leaf is that. So let's look at one more problem. The area in square feet of a rectangular stage has been widened by x feet. It is represented by that. Use the distributive property to factor the expression. What does each factor in the equivalent expression tell you about the stage? Okay, so we are factoring this. So we have 1900 plus 76x. Okay, we need to find the greatest common factor of 1900 and 76. So I'm going to start with 76 because I know that math problems that look really hard really aren't going to be all that hard. So I'm going to take 1900 and I'm going to divide it by 76 and I actually get 25. Okay, which means that 76 is probably our greatest common factor. And then we do 1900 divided by 76 and 76x divided by 76. 1900 divided by 76 is 25, or 76 times 25 is 1900, plus 76x. These cancel out. We're left with just x. Okay, so we factored that out. So what does each factor in the equivalent expression tell you about the stage? Okay, so we are the length of the stage or the width of the stage. These are the length and the width. Length, width. To find the area of the whole stage, right? Length times width. When a number is out here, it means when a number is out here, it means we're multiplying. So it means that 76 is either the length or the width. And whatever the 76 is not means that the 25 plus x is. So if we put 76 is the length times 25 plus x is the width, or we could do 25 plus x is the length times 76 is the width. That's what it means about the stage.